All right, so Natalia and I came up with this method to differentiate them. And so there are three types. There's unable to tolerate, can tolerate a conservative change, and can tolerate a highly variable change. All right, so for unable to tolerate, if you look at the question 18 in the book, then you will see, like, for example, does everyone have their book with them?
Yeah, I have mine.
Everyone else good? I don't want to like leave people behind, and I'm totally good with just sharing the screen. Here, I'll do that real quick. So if we look at question, admit. All right, so if we look at question 18 here, right, we see this chart of like different amino acids. And so the unable to tolerate would be stuff like this 6 here, position 6 here, which is all glycine. So clearly only glycine works in that area, otherwise there'd be a change. And then also position 9, where only valine works. None of the others have this like constant strength, constant amino acid in that area. Conservative change is whenever you have like the same type of amino acid. So 2 would be a good example of this, right? Isoleucine and leucine are essentially the same amino acid. Let's be real. Tyrosine and phenylalanine have big bulky side chains. Same with isoleucine and leucine. So we can be pretty certain that what we care about is that there's nonpolar side chains. 3, for example, phenylalanine, alanine, phenylalanine, serine, tyrosine, and aspartate. Honestly, I'd say that's pretty variable. Or sorry, glutamate. Just because of the glutamate. But yeah, so conservative would be like 2, and then highly variable would be you basically have a mixture of polar and non-polar because it doesn't matter. So yeah. What about another problem? What do y'all think is going to be a good good problem to work?
Probably 28.
28 of chapter 5?
Yeah.
Look for that one real quick. All right, there's one so CMBR, which cleaves polypeptides after met residues. I'm looking at the wrong one. Sorry. I'm looking at the answer and I'm like, why does this not make any sense? Okay, we wish to determine the sequence of a polypeptide with the following amino acid composition. Right, so it has 1 alanine, 4 arginine, 2 asparagine, 3 aspartate, 4 cysteine, 3 glycine, 1 glutamine, 4 glutamate, 1 histidine, 1 lysine, 1 methionine, 1 phenylalanine, 2 proline, 4 serine, 2 tryptophan, tyrosine, and 1 tryptophan. All right, so it is asking us what is the maximum number of peptides you can expect if you cleave the polypeptide with cyanogen bromide. Okay, so this is one of the proteases that they use. Cyanogen bromide, I believe, messes with methionine. I could be wrong, let me check.
That's right.
Okay, so I'm trying to find in my notes where I have that. Yeah, okay, so CNBR is one of the enzymes you're supposed to know, and that cleaves at methionine, right? So what is the maximum number of peptides you can expect if you use that, right? So there's one methionine, right? So if we have our protein, right, you're going to cut it into two pieces because you're splitting after the methionine, so you're only going to be able to cut into two pieces unless you have the methionine on the C terminus, right? So if you have methionine at the end, right, it cuts after methionine. So if there's nothing after methionine, it can't cut. So you only have one polypeptide. B, maximum number of peptides you can expect if you cleave it with chymotrypsin. That is one, I believe, that cleaves after the aromatics. Right? I am correct about that. Yes, chymotrypsin cleaves after aromatics. All right, so when it comes to the aromatics, right, alanine's not, arginine's not, aspartate, glycine, glutamine. Histidine isn't counted as an aromatic, is it? I don't remember.
I
I don't think it's counted for this one.
Okay, so phenylalanine, right? Tyrosine, that's aromatic, and tryptophan, that's aromatic, right? And so you should be able to get anything between, so you have 4 different cutting points, right? So you should be able to get 5 to 1 polypeptide. Or no, you should be able to get 5 polypeptides normally, right? But if they're right next to each other, you could get 4, 3, 2, or 1. Right? Because you could have a situation where you have like a whole bunch of amino acids here, and then you have aromatic, 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 right? But I doubt that is what the book answer says. So this is what problem? 28? Yeah.
The book says that if one of the residues was at the C terminus, it would yield 4 polypeptides.
Okay. So yeah. So it should be 5 or 4. Okay. So I guess the best way to figure out these kind of problems, right, is to know your enzymes, right? Know the enzymes used to break these bonds, and then take the number of fragments you should get minus 1 for one of them being at the C terminus. So yeah, and then C is analysis of the intact polypeptide reveals that there are no free sulfhydryl groups, right? So sulfhydryl groups are the SH you find on cysteine. Right, so it's this little thing here. And if you remember, because we've gone over this plenty of times, the sulfhydryl groups can take an oxygen, right, take off that, make a water, and form a sulfur-sulfur single bond, right? So the question says that there are no free sulfhydryl groups, meaning that all of them are involved in this disulfide bond. And we have, how many cysteines? 4. All right, so 4 cysteines leads to 2 sulfur-sulfur bonds, so it should be 2. And then D, how many different arrangements of disulfide bonds are possible? Okay, so I have 1, 2, 3, 4. Cysteine 1, cysteine 2, cysteine 3, cysteine 4, right? I can have 1 to 2, 1 to 3, and 1 to 4. And boom. I can have 2 to 3. So I can have 1 to 2. Excuse me. Sorry, I need to start this over real quick. All right, so cysteine 1, 2, 3, 4. I can have 1 to 2 and 3 to 4. I can have 1 to 3 and 2 to 4. Or I can have 1 to 4 and 2 to 3. Only possibilities I can have, right? So 1 to 4 and so 1 to 4, 1 to 2, 1 to 3. So I can make 3 different arrangements. I am correct about that. I am not. Okay. Another way to think about this is so you take the first cysteine, right? And you have 3 different results for what that can bond to, right? You take out 2 of them, then you have your last cysteine. You take your next cysteine, only has 1 bond to go to. All right. Now let's say we had more than 4 cysteines. Let's say we had 8 cysteines. How do we do that? Well, so we take our first cysteine, right? That cysteine has 7 cysteines that it can bond to, right? So that's 7. All right. Then we multiply that by the next number. Now, if we have 8 cysteines, right? We've already taken out 2. So we have 6 left. All right. So we take one of those cysteines remaining, right? That gives us 5 possible, minus 1, that's 5 possible arrangements, right? So we do that. That gets rid of 2 more. So we're down to 4 cysteines, minus 1 for the bond gives us 3. All right, so now we're down to like 1 cysteine. Sorry, now we're down to only 2 cysteines, right? Minus 1, that gives us 1 possible arrangement. Multiply that out, you'll get the number of cysteine residues. Do y'all see why that's the case? All right, okay. So what's another good one? We could try, wait. Okay, we could try, let's see. Oh, I'm looking at the wrong version. I keep looking at the answers and not the questions. And so I'm like, why is this the case? All right, so do we remember how to do problems relating to size exclusion? Actually, wait, let's do, Natalia and I did this problem earlier, but I think this is something he might show. He might do on the test to kind of throw us off a bit. It is question 12 on chapter 5. And so basically this question is saying that whenever you do SDS page, right, you get a molecular weight of this protein that corresponds to like 200 kilodaltons. And a dalton is just a gram per mole. So it's just a unit of molecular weight. But whenever you do gel filtration, you get a molecular weight of 800 kilodaltons. And so the reason for this, right, if you remember in SDS page, right, we treat our protein with 2 mercaptoethanol, right, and that looks like this, something like this. And that gets rid of the disulfide bonds, So it makes it so that our protein, each different part of our protein separates. Well, given the fact that in SDS we have 200 kilodaltons, but in gel filtration we have 800, right? We don't do the 2 mercaptoethanol in gel filtration. So that leads me to believe that our protein is actually 4 identical subunits, all 200 kilodaltons in size, right? But 200 times 4 gives us 800. So I think he might try to throw something like that at us on the exam. Can't say for certain, but that's what it looks like. Any other good problems y'all think of? If not, I'll just kind of do a random one. All right, so let's do, all right, so question 1. This is a pretty simple problem. So basically it's saying, oh, we have a chat. Do you think he'll do fold purification? I am not actually sure what fold purification is. Did we talk about that? I remember he did, he very briefly said something about like hydrophobic purification, but he said that was really bad. And that's all I have written down about that. What do you mean by fold purification?
It has to do with like it was the one that had the table in the book where it had like the crude extract and the specific activity. And then you find like the specific activity for each and then divide them. Like fold purification.
Can you show me, can you point me to a figure in the book? I'm having a hard time visualizing that.
Number 26 is what it is.
Number 26, all right. Contains that many per milliliter. 10 microliters of extract, catalyzes the reaction rate of that. Form per minute. The extract was fractioned by ammonium sulfate precipitation. A fraction precipitating between the solution contains 50 milligrams per milliliter of protein. 10 microliters of the purified fraction catalyzes the reaction rate of that. What is the degree of purification? I'm honestly not sure. He didn't go over that in class, did he? Because he said that we shouldn't be going over, or he said that we shouldn't have things that weren't in class. Let me see. 26. That should be. I mean, I have the answers from the book, right? But it's basically, so what the book says. So what the book says is you take, so we have 32 milligrams per milliliter. Hang on, let me look. I would doubt that this is going to be on the test because I don't remember at all him talking about this. Do y'all?
No, I don't. I know he talked about purification, but not like that.
It's like I don't even have anything about that in my notes. He talked about like the only real type of purification we talked about was the chromatography types. with like the affinity chromatography and the immunoefficiency chromatography and the metal affinity and the ion exchange. So I would say don't worry too much about that. I feel like that might come back to bite me in the ass, but we'll see. Yeah, anything else? Looking at the wrong one again. Okay, so we have a cool. I haven't really like worked that problem because I kind of looked at it and I was like, well, there's no way this is going to be a case. No way he's going to have a problem like this. One problem I did see on this. So you remember how last time we had that like PI, or we had the titration curve problem where we had to draw the thing out? Well, it looks like we're going to have a, the thing he's going to make us draw out this time is going to be, I believe it's SDS page that has this relation where the log of the molecular weight is going to be proportional to the, I forget actually. Hang on, let me take a look at this real quick. So how much the, so an SDS page, right? So an SDS page, right? The log molecular weight is proportional to the mobility of the proton or of the protein. So he's gonna, what it looks like he did in previous years was he gave the molecular weight to you in like kilodaltons. Remember that this is just gram per mole. The Dalton is gram per mole, so this is like kilogram per mole, and just convert it to Daltons. But so it should be a linear relationship between the log of the molecular weight and the mobility. And so the way that I would do it would be, let me open the test real quick, see exactly how he wants, how he had us, what information he actually gave to us. I'm opening up exam 2 here. And it is question 3B. All right, so what he did on the test, right, was he gave us these like, he basically gave us like little markers. Here, let me actually share the screen for this because it's going to be a lot easier if I do that. All right. Here we go. All right, so this one here, right? Do y'all see how there's like little marks here? What I would do is basically say this is 0, this is 1, this is 2, this is 3, 4, 5, 6, 7, 8, 9, 10, right? And whenever it asks you to plot the molecular weight, you just go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? And then plot the logarithm, log of the molecular weight and the mobility on the x-axis. So yeah, that should be the case. Sorry, my throat is giving out. Okay, what else would be a good idea to know?
And also just on that problem, I actually spoke to him about it because whenever I did it on my own, I got like different answers. And whenever you calculate the like C and D, If you're just like, you know, like 0.1 off, like that's like a huge difference. So he said that he will like have some leniency on that question, but not much. Like, figured I'd let y'all know that.
So C and D, right? C is asking you to find the approximate molecular weight of band 1. D is asking you to find the approximate molecular weight of band 3. So what I've noticed, so I looked at the key for this exam, right? And I noticed, so you got to be very careful, right? But, oh no, never mind. This is really dumb. Okay. So he basically wants you to go like very close. So yeah, be careful. Draw your curve very well. One thing that you can do is you can figure out the equation of the line and do that, but that's going to take up too much time. That'd be something I'd say if he wasn't giving us a test that was longer than we should be able to finish. But yeah, so okay, what I would do is I would put the, so like it's going to be 10 to the power of something. I would put that down, right? Say 10 to the power of like 4.55. Put that down, put what that's equal to, right? And then he can be a lot more lenient on you because he can be like, oh, well, you were just 0.1 off.
Exactly. Yeah, because I just scaled mine differently than he did. So mine was just slightly off, but it was like a huge change in the final answer. But he said it was still okay.
Basically, he just, what he's trying to test there is just, do you know the relationship between the logarithm of the molecular weight and the mobility? Can you go from the mobility to the molecular weight? And because it's logarithm, it's going to be annoying. It's going to be annoying, but you know, just give him reason to believe that you know what you're doing, right? All right, what about another problem?
I think you had asked something about 25 on chapter 5.
25 on chapter 5, all right. So purification tables are often used to keep track of yield and purification of proteins, specific activities, the ratio of the amount of protein interest in the case of MB, obtained at a given step, per enzyme units divided by the amount of the total protein. The yield is the ratio of the amount of protein in a given step divided by the. So I'm not sure that he's going to ask anything because this is the folding purification thing, and we didn't talk about that at all. And I don't see anything like that on the previous exams. It's like,
But exam 1 was not like the previous exam either.
well, he at least covered everything in exam 1, right? Some of it you had to like think about, right? But there were no new concepts. I guess probably a good thing to remember is in your alpha helices, right? Remember the 3.6 residues per turn. And the 1.5 angstroms per residue. I mean, I'm almost. I would bet that he's gonna ask something about that. Oh, and it's 5.4 angstroms per turn. If you just multiply it out, and then if the polypeptide is extended, right, then that is 3.6 angstroms per residue. Or no, it's 3.5 angstroms per residue. My bad. don't remember if he gave us the 3.5 angstroms per residue, but that was in the biochemical calculations class. All right, what else we got? Oh, God. Okay. Let's see. I mean, that's pretty much it for exam. Well, I guess the size exclusion column. If you take a look at, here's a good size exclusion problem. Was the alpha helix really chapter 6? Yeah, I guess it was. Okay. Honestly, let's just head on to chapter 6. So taking a look at stuff we've done, I don't think we've done all of chapter 6 yet, have we?
No.
I looked through the book for it, so a lot of my stuff's just additional information if you're looking at like my notes. But we don't need to know anything about protein stability. Even in lecture today, he skipped over it.
Skipped over it. I think there may be a question regarding like I feel like there may be a question of like what forces make a protein stable, right? And that's like, you know, like hydrophobic, charge interactions, and like disulfide bonds. Can y'all think of anything else? Didn't he breezed over that really quick though.
No, this book it said that van der Waals was it helped in stability just because when it denatures, like they form short chains. So whenever it denatures, they get disrupted. So those aid.
Mm-hmm. So I think van der Waals would be hydrophobic, right? Or no, wait, van der Waals is included in charge. Because I wrote down the 4 he talked about, and it was like hydrophobic effect, electrostatic, disulfide, and metal ions. But I guess he can't really take off points if you put something extra, right? So van der Waals. Can y'all think of anything else that would be like a use, like something that would stabilize a protein? I mean, like, because most of this stuff, because like most of the stuff I can think about, like hydrogen bonds of the backbone, that's charge, stuff like that. But yeah. So what is a good chapter 6 problem? Like, what do we think is going to be in chapter 6? So do y'all remember what which one is phi and which one's psi? So y'all remember that the alpha carbons are basically like pivot points, right? And you go to the CO2 or C double bond O and H, right? You've got like one plane here and then like one plane here. Do you remember which one of these is which one of these is phi and which one of these is psi? Because I feel like he might ask something about that.
He said that the bond between the N and the alpha carbon is phi, and then the bond between the alpha carbon and the carbonyl, or the, yeah.
Okay, I have these Greek letters, right? Because I'm really shitty with Greek letters. Psi is the pitchfork, and phi is the sideways theta. I'm gonna just Google
Yeah, you're correct.
phi. Okay, phi is this one, and psi is this one. Okay. Because I am really not great with Greek letters. I basically only know theta by repetition at this point. So we talked about, there is a diagram that he talked about, and it was the Ramachandran plot. Ramachandran plot. And it was basically, you know, this like graph of all possible phi psi values, right? So psi would be right here. And phi would be right here. Or psi would be there, phi would be there. Okay, I need to get better at that. Okay, so, and he said that we don't typically have phi values that are positive, right? So over here would be like minus 180, and up here would be 180 and 180, right? This side of here just really isn't stable from what he said. So we don't worry about that. So phi is usually always negative, and psi has a lot of different values it can be. So what he said is basically you can have like really low values. You can have like sort of intermediate values that work. And then you can have basically all these values. Do you remember what, did he talk about the amino acids that are more likely to form these?
I don't know about that one, but I do know that the only one that can form outside of what's like in the plot is glycine, because it
Yeah, glycine, there's like no steric hindrance. I feel like he might ask, show what types of like steric hindrance there might be. So let's see. Ba-doop. Right, so like the R groups mess up, but the R groups are sterically hindered of each other when it's over here. But if you're glycine, then your R groups are both hydrogens, so you don't care. He talked about how the amide bond, right? If you remember from CHEM, the amide bond, the amide has a sort of resonance stability or resonance structure that looks like this. Right, and so there's two conformations, right? Cis and trans for this thing, right? Cis where the alpha carbons are on the same side, trans where the alpha carbons are on opposite sides. All amino acids are trans. Pretty much all of them are in the trans, quote unquote, trans conformation, except proline. he said about 10% of prolines are cis. And it's because a proline kind of shunts the R group up out of the way. And so you can have a bit of so it's lower energy. So it's lower energy to have a cis proline than it is to have pretty much any other. So yeah. All right, let's look at some problems. What would be a good one? I guess number 1's all right. So number 1's asking us to draw a cis peptide bond, right? And I feel like this would be an easy problem for him to give. So we have the C-double-O, right? And then the N with the C alpha coming out here, and then hydrogen coming out here, right? And so we see that there's going to be some steric hindrance between these two. Whereas if they're on opposite sides, it wouldn't be as big of a deal. You know, like this would have an R group here, you know, R group coming out here, that stuff. So what about like number 2? Is number 2 a good problem? Let's see. How many peptides? No. Number 3. Ooh, okay. Number 3 seems like a problem that he could give. So he gave that kind of DNA that DNA enzyme problem on the last test that was really stupid. That was like the one question I missed just outright. Because I was like, oh well, obviously it's going to be basic. So I was completely wrong. But so number 3 is asking, why would you be unlikely to see a helix, so an alpha helix that contains only arginine, lysine, methionine, phenylalanine, tryptophan, tyrosine, and valine. All right, so why do y'all think we would why would we be unlikely to see a thing that contains these amino acids and only those?
Because of the aromatic structures?
So yes. So part of it is that, right? So tryptophan is big and bulky, right? Tyrosine, same way. The valine isn't too bulky, right? The phenylalanine is big and bulky. And so what you get is basically this helix, right? But all the stuff kind of pops out. You know, you have the phenylalanine right here, and you've got like the tyrosine right here, and they kind of interfere with each other. You know, they have some steric hindrance here. So basically, we see a lot less. We would need some like smaller side chains coming out. So something like alanine, right? If we had that, that might help. I mean, also, we do have a lot of nonpolar side chains here, and those don't typically like to be in alpha helices by themselves. And I'm guessing that it doesn't look like the book says that's an answer, so we won't worry about that. Okay, what do we think about question like, what do we think about question 5? That's an interesting question. So it's basically, so chapter 6, question 5, is asking, so we've got a digestive tract of a moth, basically. It's a strongly reducing environment. Why would this be beneficial? Well, if you think about it, right? So what have we been talking about in this chapter, right? Proteins. So what does reducing have to do with proteins? Well, if you remember the disulfide bonds, right? This was an oxidation. So going from 2SH right, going from this to this was oxidation because you're losing two hydrogens, right? And so if you have a strongly reducing environment, right, you're breaking those disulfide bonds in the digestive tract. And it says that it's a clothes moths, right? So clothes have a lot of disulfide bonds in them, right? Because essentially most fabrics are just a bunch of proteins that are like bonded together. And so if you can break those disulfide bonds, then you can get, so by having a reducing environment, you can break those disulfide bonds and make it easier to digest those proteins. All right. So do we have any other good problems? What do y'all think?
I do just have a quick question about number 4. Did he ever say anything about the angstroms per turn for keratin?
So let me get to that problem real quick. Okay, so number 4, calculate length of angstroms in a 100 residue segment of alpha keratin coiled coil. All right, so keratin, right? It says that it's an alpha coil. So it's an alpha helix. So an alpha helix, right, is, he told us that those have a 3.6 residues per turn and 1.5 angstroms per residue. So 5.4 angstroms per turn, right? So it's asking us for a length in angstroms of 100 residue segment of the alpha keratin coiled coil, right? So it's 100 residues time over 1 times 1 turn per 3.6 residues times 5.4 angstroms per turn. So calculate that out and you get the answer. So yeah.
Okay, and I actually just found it. It's in chapter 6, and it says that keratin has a helical spacing or pitch of 5.1 angstroms instead of 5.4.
Okay, then he did not go over that in class. So I don't think he'll ask something like that.
Okay, because I do remember him going over keratin and collagen, but I just
he did it in Pymol, I remember, but he didn't like talk too much about it, which was weird.
But didn't he bring up the coiled coil?
Yeah, he brought up the fact that like keratin is a bunch of alpha helices coiled around each other.
Okay.
But I feel like he didn't. Did he go over it in class?
He did, because I don't have that specific part highlighted, but I highlight all the stuff he goes over, and I did highlight the sentence that came right before that, so I feel like he might have like mentioned it.
Okay. So I might need to go back and look at his lectures again. Y'all, COVID sucks. Don't get COVID.
You have COVID?
I think I have COVID at least. I've got the symptoms of it. I got
No.
tested today,
All right.
which sucks. But the show must go on. So, so we remember, okay, so there are a couple different types of proteins he wants us to know, right? So remember that there are two types of proteins, roughly. There's fibrous and globular, right? Fibrous are like long strands, usually that like wrap around each other. And then globular kind of look like that. If you remember from biology, I remember talking about this in biology. I don't quite remember, but you know. There are two types of fibrous proteins, right? Or two fibrous proteins that we need to know. Keratin, which consists of a 7 amino acid repeat. And he didn't give us the sequence of it, so I don't think we need to know that. But so if you lay it out like A, B, C, D, E, F, and G. 1, 2, 3, 4, 5, 6, 7. Okay. A and D will interact, and they will be the only ones to interact. Have fun, Natalia. Okay. So A and D will interact, but none of the rest of them will. And and then collagen. So right, so keratin is a sort of braid of multiple fibrous proteins that are all alpha helices, where collagen is 3 polypeptides in an actual braid, right? So my girlfriend taught me how to braid hair the other day, right? And that's basically the same structure, right? So you have like a third, yeah. Okay. So I'm at about my limit right now. I'm a bit, the medicine's wearing off right now, so I'm gonna have to go. So I think the next meeting will probably be, we could probably do something on Tuesday if y'all want. About what time would work for y'all?
Same time, doesn't matter.
Because I have lab until 8. Yeah, microbiology lab. It's fun. But it never lasts until 8, so probably earlier than 8. I'll send a message in the group chat. Then, Wednesday and then Thursday. Oh, Lord. What do y'all think would be best right before the test? Like going over the previous year's exams or what?
Maybe, yeah, the previous exams and then the biochemical calculations, maybe.
Okay, so I'll try to have those printed out for Wednesday and Thursday. And then, yeah, there's still stuff we haven't covered, which is kind of annoying me.
Yeah, I was about to say maybe on Wednesday we could do just a session just going over the stuff he went over on Wednesday.
Yeah. I do have a bit more time on Wednesdays than normal, so I could probably start a bit earlier. Ooh. All right. Okay. So I will keep you updated in the group chat. Y'all have fun. Peace.